Good morning, everyone. Today we come to lecture 11. We still are on group theory. And this is the third lecture on group theory. To begin with, let's review what we learned last time. So last time we proved this great orthogonality theorem. So let's review what this theorem says. The great orthogonality theorem says if we consider all the inequivalent, irreducible, and unitary representations of a group, representations of a group, then they follow this orthogonality relationship. And here R is the element in the group, and then gamma is a irreducible representation. And I and J are the index for the irreducible representation. And here mu, nu, alpha, beta, they represent the elements, the rows and the column of the matrices. So when you make a summation like this over all the group elements, then you have this orthogonality relationship. So you see three delta function here. So the delta function ij means if they're not in the same representation, you get 0. Mu alpha means if they're not in the same row, you get 0. Nu and beta means if they're not in the same column, then they're 0. So basically, if they are not like in the same element, okay, then you'll get 0. So Li here is the dimension of the representation, and H is the total number of the group elements. Is the total number of group elements. So this is the central theorem in group theory. So let's understand this. Let's try to understand this theorem. So we'll consider the geometric interpretation. Okay. So what is the geometric interpretation? So from this summation here, okay, let's recall what we learned in the basic like inner product between two vectors. Suppose you have a dimension, like three-dimensional space, x, y, z, and then there are two vectors. Let's say there are two vectors. Okay, vector 1. Okay. Okay, so here you have x1, y1, z1. So this is a vector 1. Then you have another vector. Let me use this color. Okay, you have another vector. Okay, let's say like something like this. Okay. Then so you have v2, x2, y2, z2. I mean, you can have many of them. Okay. So this may not be a good example. Let me try an orthogonal one. Let me find one that is orthogonal to it. Okay, let me find this one. Okay, make them 90 degrees. Okay, so one like this, and then go back. Okay, something like that. Okay, V2, X2, Y2, Z2. Okay, so these two are orthogonal to each other. So you can have this dot this. So what do you mean dot product? Dot product means you sum over I, V1I, V2I. Okay, you sum over them, then you get 0 if V1 is perpendicular to V2. Okay, so here this sum over I basically means you sum over 1, 2, 3. So 1, 2, 3. Or you just sum over x, y, z then. Okay, doesn't matter. X, y, z. So you sum over x, y, z. So how many vectors can you find? How many vectors can you find to be perpendicular? The maximum number of orthogonal vectors is 3. Is 3. In a 3D space. In a 3D space. So this is what we learned before. So here, let's go through this. So what is this thing? This is basically inner product summing over R. Summing over R. So how many elements? So you can have something like this, but for group element R. Okay, so let me use this group element, let's say R1, R2, R3, like a group element. Group element space. So you make a group element space. So of course here I only use 3, but in principle you can have many. Then you go to H in it's a H dimension. Is a H dimension space because the total number of elements in the group is H. So it's a H dimension element. Okay, so in principle, you will have a vector like this. Okay. So let me use a dot dot dot. Okay, dot 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 dot. Then you have H. Okay, so you have a n dimension. So how many number? How many number of orthogonal vector can you have? So you just copy this statement. The maximum number of orthogonal vector is H. In a HD space. In HC space. Okay, so from this we can already draw a very important conclusion of the group theory. So how many what is the total number of let me see, so the maximum number of orthogonal vector is H. But here, if you counted this row and column indices, they are the indices for the vector. So this one is equivalent to what? Is equivalent to this 1 and this 2 here. Okay, is equivalent to 1 and 2, and the R is equivalent to this XYZ. Okay, so here, if you make a comparison, mu VI, and then you have a VI XYZ. So you can make the comparison. R draw this is R XYZ. So this one corresponds to this. And then let me use a different color. This let's say mu VI. So this is the I. So this one and this one correspond to this. Okay. So the index for the irreducible representation and the row and column indices, they correspond to this index for the vector here. So here the total number, the maximum number of I is smaller than the dimension. Nullity. So here you can see what is the total number of I here. So mu V, totally you have Li. So let's say Li is the dimension of this irreducible representation. Then you have Li square is the number of matrix elements in gamma I. So if you sum over all the irreducible representation, is the number of matrix elements in all of them. In all irreducible representation. Basically you just group them together. And this need to be smaller or equal to H. So this is a very important conclusion. So basically that means if you have a group with a finite number of group elements, you are not going to have an infinite number of irreducible representation. The number of irreducible representation will certainly be smaller than the number of group elements. Okay, so that's very important. If you want to have infinite number of irreducible representation, then your group need to have infinite number of group elements. So for the point groups that we study in solid state physics, the point group, they all have finite number of group elements. So they will all have a finite number of irreducible representations. And later, we will prove that is actually equal relationship. Is actually H. Later we will do this. But right now just take it. So that's an important result. Let me give you an example. So in the last lecture, I gave you an example. Okay, this D3 group. Okay, this D3 group. So the D3 group has you can use it. You can use a triangle equilateral triangle. Okay, so how many group elements? You have a E. My drawing here is not very good. Okay. So you have UA, rotation on A. I forgot which one is A, which one is B. Okay. Anyway, I hope you get it. So this is UB. So UC. So this three means the rotation along this three axes. Then you have a C3 and C32. So totally, C3 means rotation by 120 degrees. C32 means you do it twice. So there are totally 6 elements. There are totally 6 elements. Okay, so let's consider how many number of irreducible representation can it have? There are totally 6. Okay, there are totally 6. Suppose there are some possibility. Okay, let's consider possibility. I mean, given the restriction of this restriction. So, I mean, one possibility. One possible. Okay, let's consider possible. Configuration of irreducible representations. I mean, first is 1, 1, 1. Okay. Yep. Let's say possibility 1, 6, 1D gamma. Okay. You have 6 of them. Then summation. This is just 1, 1, 1, 1, 1, 1, 6. Okay. I mean, the later we show that that won't be the case. Okay. The second one is you assume one of them is 2 dimensions. So once you assume then is a 2 dimension, like 2. Let me. Sorry, 1, 1D. 1, 1DI. And then the other must be 2. Sorry, 1, 2D, 2D, 2D. Yeah, 1, 2D. Once you set 1, 2D gamma, then what is left is only 1, 1D. Because once you set 1 to be 2, then what is left is only this. Okay, and 3D gamma is not possible. 3D gamma is, I mean, gamma means irreducible representation, because 3 square is larger than 6. Okay, it's large. So that means if you have a representation, gamma is 3D, then it must be reducible. It must be reducible. Is that okay? In another way, another conclusion that if a Hamiltonian has a symmetry group D3, like a 6 elements, then then it won't have a threefold degeneracy. A threefold degeneracy. Okay, so in order to have high degeneracy, you need to have a high symmetry. So if you have a system only with a D3 group symmetry, then you should not expect that you see a threefold degeneracy in the system. Because I mean, later we'll learn this in more details. The basis function of those eigenfunction, they are the basis function for the representation. Okay, if your representation, the eigenfunctions are the basis function for the irreducible representations. Later we'll learn more about this. So if you have a symmetry group with only 6 elements, then it won't produce the symmetry won't produce a threefold degeneracy. Okay, so later we'll have a more of this knowledge about the property of the group, and then we can identify that this is the only case. The first one won't. The first one is usually the cases for the abelian group. Okay. So any questions before we move on? So let's move on. Okay, let's move on. So if you have a irreducible representation, gamma I is a irreducible representation, then you have a similarity transformation is also a irreducible. I just use IR to represent it then, okay? Because we're going to write this irreducible representation again and again. So that means basically this corresponds to a change of your coordinates. Okay, you change your coordinate, then the form of the matrix, the element will change. But for us, we don't want to be bothered too much by using different coordinates. So both of this for us, they're just equivalent. But when you apply this on the orthogonality theorem, then they will give you a very different number, right? Because in the orthogonality theorem, what you will see is this exact element. If you make a change of coordinate, this element will change. I mean, of course, the orthogonality relationship still hold, but we want to make it simpler. So there's something that will not change even after you change the coordinate. That is the trace. The trace. So what is a trace? Suppose you have your R, so you get the trace. So this trace is when you take the mu element, you make it go to Lj, and mu. That means you sum over all the diagonal elements, you get the trace. And we give a name to this trace. We call it the character. We call it the character. We use a chi to represent it. We're going to define as the character of R of gamma R. Or just R then, just the R. Or just R. In the jth representation. Here the gamma can be reducible or irreducible. It doesn't matter. Okay, so this is the character. Character is the trace. So if you make a transformation, let's say you you make a transformation like this. So what is the character? Okay, then you just get the trace. Yeah, you get the trace of this one. Let me make it into J then to be consistent. Yeah. Then by using a linear algebra, you'll find that they are just the product of the trace. Okay, they're just the product of the trace. Okay, and then these two will cancel each other. Okay, these two will be equal to 1. So eventually, eventually you're going to get back the same thing. So that means the character remain the same after similarity transformation. So the character is a more convenient thing to use. Okay, then we're going to derive an orthogonality theorem in terms of the character. Okay, in terms of the character. So let's go back and take this orthogonality theorem. Okay, let's go. Okay, so this is the orthogonality theorem. So we're going to set mu equal to nu, alpha equal to beta. Okay, we're going to set it. So after you set it, then you just make it, this will be mu mu. This will be alpha alpha. So then this mu mu, this will be mu alpha. Okay, you just change them into mu alpha, and then these two are the same. So so you only need one of them. Okay, you only need one of them, and then sum over mu and alpha. Okay, if you sum over mu and alpha, so let's do it. Copy. Sum over mu and alpha. And here you sum over mu and alpha. After you sum over, let me see, what will you get? Then this one will simply become the character. And then this one will be the character, J. Okay. So you get the trace, right? You sum over. And then here, let me see. When you sum over, then you're going to get 1. You're going to get 1. Because eventually you're going to sum over alpha, and then this is just 1. Okay, because you're doing the summation on the delta function. So only when mu equal to alpha, you get 1. When mu is not alpha, you don't get 1. So this is just 1. So eventually, what is this? this will only become the number of, let me see, this is the dimension. It will become the dimension. Because you are doing this on a representation with dimension Li. So after you summing over all of it, then you only get Li. Okay, so eventually you get this result. The character. Oh, sorry, this is I. This is I. So I, and then J, and then this is H over Li, and then delta I. Okay, so this is the orthogonality theorem for the character, Okay, later we'll also notice that all the elements in the same class has the same character. So you remember what a class means, right? So so if let's say R1 equal to R2, let's say you have A and A -1, then they are in the same class. If you can write them. Then what is the representation? Okay, then you get the representation. The representation will be gamma R1 equal to gamma mu. The representation follow this, right? Follow this relationship. Okay. Then you take the trace. So the character of R1 will be the trace. Then you get the trace. And then you can change this to here. And then the trace of these two inverse matrix will be inverse to each other. This will get 1. So eventually you get this. Okay, so if two group elements in the same class, then they will have the same character. Okay, so that means you don't need to sum over every element. You don't need to sum over every element. You only need to sum over all the class. Okay, so I use a symbol. I just take this the symbol C. Let me write this symbol better. Okay, how to write it? Yeah. Okay, this is a fancy form of a C. Okay, means a class. Denotes the kth class. The kth class. So this one, instead of summing over the group element, you just make them sum over K. Then you don't need to consider the character for each group element. You just need to consider the group elements of each class. Okay. Then of course you need to multiply the number of elements with nk elements in the class. And then sorry, I make a mistake here. This li is not here. This li is not here because it get canceled out here. It was already canceled here. So this is just h. So okay, so this is the result that we will use quite often. Okay, so this is the result. Let me just highlight it. Okay. So this is the orthogonality theorem in terms of character. So basically, you get the character for each class, and then make an inner product, and then weight it by the number of elements in the class. Then you get the orthogonality relationship. Okay, here you can see that this represent, okay, this one. Let me just copy, okay. This can be viewed as a vector, as the jth vector in the class in the class space in the class space with a k dimension. With k dimension, because you're summing over k now. Okay, so it looks like you are doing like a k, like class 1, class 2, class 3, dot class k. Okay, then you have this element. These are the vector. So the total number, the maximum number of the orthogonal vectors in a KD cannot exceed k. But here there's only one index. That is the number of representation. So this I and J are the index for the vector. So that means the maximum number of irreducible representations is smaller or equal than k. Than the number of classes. Than the number of classes. And it can be proved that prove that the equality holds. The equality holds. So basically, here I don't have the proof for you, but it can be proved. Okay, you just take the result for now. So the maximum number of irreducible representation is the same as the number of classes. So if we go back to this relationship, to this so this example. If we go back to this example, let me just copy this. If we go back to this example, you know that there's only one possibility. So you know that this example, this example won't hold, because there is only 3 classes. So you can separate this into 3 classes. Okay, so 1 classes. You can separate into 3 classes. So one is E, the other is UA, UB, UC, and then the other is this. So there are only 3 classes. And you can use a name. You can use this class 1, class 2, class 3 to represent them. So this 1, 2, 3 is the K index. And usually people will add a number here, 3, 2, to show the number of indices. So to show the number of indices. So you can expect that this is the only possibility. So what you will expect is this. What you will expect. We expect a character table like this. Of D3 like this. So usually when you draw the character table, you draw it like this, okay? And then here you have class 1, 3, class 2, 2, class 3, okay? And then here you just have representation 1, representation 2, and representation 3. So what is the character for representation 1? Is usually just the identity representation. What do you mean identity representation? Means you use unit matrix for all of them. Means unit means all are unit matrices. Basically means for all of this operation, it remains to be the same. Okay, let's say you have a number. Then no matter how you rotate your system, reflected the number won't change. If you have a vector, you rotate it, the vector will change. But if you start with only a number, then it won't change. So if a certain quantity never change under any symmetry rotation, then it belongs to the identity representation. So for identity representation, what is the character? Then it's always 1, right? So you can fill in all 1. So the character will be 1. This one is still 1 dimension, because we already know that you have 1 2 dimension and 2 sorry, you have 1 2 dimension and 2 1 dimension irreducible representation. So the second one is also 1 dimensional representation, and this is the identity element, right? So the trace is always 1. Is always 1. For this is a 2 by 2 matrix. So for the identity element, it is 2. Okay. So just from the orthogonality theorem, we can already write down the first row and the first column of the character table. So what is left are 2 more. Okay, are 2 more. So let me just write it out for you then. So the other 2 is this is -1, and this is 1, and this is 0, or -1. Okay. So let me see the relationship. You can already see from there, you can examine. Let's say the first row. The first row is this. Okay, the first row. Let's check the orthogonality. Let's check the orthogonality. So the first row is this. Let me just copy this. Let me just copy the whole thing then. Okay. Okay, if you only consider these 2 rows, then you will see that 1 times 1 and 1 times -1 times 3. You need a times 3. And then 1 times 1 times 2. Then you sum them together. What do you get? You get 1 minus 3 plus 2. You get 0. So this is our relationship here. This is this relationship, this one. Copy. Let me do it like this. Then you can. Okay, so this is the relationship. So you just compare these 2 to here. This 2 to here. And then this one. I mean, they're all very simple algebra. Okay, a very simple algebra. But you see they're orthogonal to each other. So let's do it one more time. Let's do it one more time. So now let's compare. Let's compare these 2. Okay, if you compare these 2, then you get something similar. 1 times 2 plus 0 times 1 times 3 plus -1 times 1 times 2. So you get what? You get 2 times 0 times -2. You get 0. Okay? Just copy. So similar. So this one. This one go here. And this one go here. And this one goes here. Okay. Okay, so you see that they are orthogonal to each other. So then one more example then. Okay. Just do 1 or 2 more times. You already get the idea. So this time this just do this 2. Okay. Then you have 1 times 2 plus -1 times 0 plus 1 times -1. You need to remember to multiply this 3 here. times 3 here. So you have 2 plus 0 minus 2, you get 0. Okay, so let me copy this again. Then okay, so what about in the same column? What about in the same? Okay, so let's do it just on their own column. Let's do it on their own column. So because this show the orthogonality, so what about if they're in the same column? If they're in the same column, then we're going to deal with this thing. Okay, if they're both I, let's say if they're both I. So according to the orthogonality theorem, they will be just equal to H. Okay, because I mean I don't want to go back and forth too often. But you check this formula. So when this is the same, then you only get H. Okay, so let's check. Okay, so let's do this. Okay, then let's say this is 1. I mean, it just times itself. So 1 times 1 times 3 times 1 square times 2. So you have 6. Okay, because this is 1, this is 3, this is 2, then you get 6. Similarly, 1 square plus negative 1 square times 3, 1 square times 2, you get 6. And this one is 2 square. Okay, 2 square times 1, then you have 0. You have, 0 times 3. You need to times the times 3 times negative 1 square times 2. So you have 4 here, you have 2 here, then you all get 6. Okay, you all get 6. Okay, so you see that the character follows the orthogonality relationship. Okay. If you know that the characters are integer, you don't even need to write out gamma. You can already know this number because you have this orthogonality relationship. Basically, once sometimes you don't need to know all of this gamma. You know some of them, then the character according to the orthogonality relationship you just know. You don't even need to know the form of the gamma. You just know the character. Okay, there's another orthogonality relationship here you probably notice. That is if you take these two and you take the inner product, they're also 0. Because here is 1, negative 1, and 0. You sum them together, you will also get 0. If you take these two, then this is 1, negative 1, and 0. You also get the 0. So the vertical column are also orthogonal to each other. But when you take the vertical column, you don't need to multiply the number of elements in the class. You just simply treat them as just vector. Okay, so this actually can be proved. And this is the second orthogonality relation for character. For characters. Okay, so now let's define a function, a matrix called a Q. Let's define this. Okay, we're going to define it like this. 1, and then this will be class 1. Let me just copy and paste then. Okay. Okay, I'm going to change this. So this will be 2. This will be 3, dot, dot, dot. Then this will be 2. This will be 2, 2. So basically, Qij equal to gamma, chi I and j. Okay, so you define a matrix like this. Then you define another matrix called Q prime, called Q prime, and also define Q prime equal to high 1 N1. N1 is the number of elements in this class. Okay, so let me copy. Okay, clean up dot, 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 dot. Okay, so let me see. We're going to change the index. This will be 2. This will be 2. 2. And then this will be 2. This will be 2. And then this will be 2, 2, 2. So basically, if you take the elements out, ij, you're going to so here the j is going to the row. The j is on the row. Okay, so this is j. Sorry, the j. Let me see. I. Then this is the j. And then this is the I. Okay, this is the J. Because this is the column index. And here the column index is the representation index. Okay, so you compare these two. They're not exactly the same. Okay, let's compare. So you compare these two. So this one is let me just this is I, J, but this one is different. This one is, this is the I, but the I is here. This is the J and the J is here. Okay, so the index is somewhat swap. Okay. Okay, so why do we define these two? We want to see the product. Okay, suppose you have Q and Q prime together. And what is the ij element of this matrix? So you can sum them together. Let's say let's say K. Okay, you have Q, I, K, and Q prime Kj. Okay. Then you just take this. You take this, copy. So here you're going to have I, but this thing is going to become K. K. Okay. Then you take this. And then let me see. The K will be I. So this will be K. This will be K. And then this will be J. Okay. And then the summation is on K. You just compare. Okay. This one and this one. So I here is the K. So this will become the K. J, this is the J. Okay. So you just use the definition. But what is this thing? What is this thing? This is just the orthogonality relationship. This is just the orthogonality relationship. This is the same thing that we yeah, so you from this. Where do I put the orthogonality relationship? Let me go back and put it here. Okay, you take this relationship. You take this relationship, and then you just move the H to the other side. To the other side, like to here. Anyway, to here. Then you have this. Okay. Of course, you take the complex conjugate, it doesn't change the result. Okay. So that means this means that Q prime is the inverse of Q, because you take this two, you get a unit matrix. Okay, so these two are just inverse to each other. Because they're inverse each other, they also commute. Okay. Because Q prime equal to Q inverse, so Q prime equal to Q prime Q. Because all the matrix, they commute with their inverse matrix. Okay, so we have already learned about this matrix element. So let's deal with, okay, so let's consider this matrix element. Okay. Let's consider this. So this one, Ij equal to, okay, so we're going to go back to this definition again. We're going back to get this definition. Q prime is this thing. Okay, get to here. Q is this here. And of course, we need to sum over K. Q prime I K Q K J. And then we're going to replace it. So Q I, the I should be here, and the K is here. And then here, this should be K. and this would be J. Yeah, according to their definition. Okay. And then we know their inverse. So we know this result already. We know this result. So eventually we just obtain this thing. Let me see. This is sum over K. Okay. Since you are summing over K, so this Ni can be moved to the other side. So this can be moved to the other side. It's just summing over K. So what does this relationship mean? This relationship means, let me make this slightly smaller. Okay. So this relationship means when you are doing, okay, let's go back to this column. This okay, this one. Okay, let's go back to this example. Let's go back to this example. Okay, what does it mean? Means this is different column. Okay. For example, let's consider 1 and 2. Let's consider 1 and 2. This is 1 and 2. 2. Okay. And then what you're doing is sum over the representation. Okay, you sum over the representation. So what you will get is 1 times 1, 1 times 1, 1 times -1, and 2 times 0. So what you will get is 1 minus 1, you get 0. This number, this is the character table. Of course, I know what you mean. Okay, this one is already got, and this one you can obtain. So the only left over is this 4 number. If you ask how to get it, of course, using the orthogonality theorem, you can kind of deduce them. However, if you don't use them, all you need to do is to find the gamma 2. You don't need to find many. You only need to find one example. Then you get the trace. You only need to find one example. Then you will be able to get these 2 numbers. Once you get these 2 numbers, then the rest are just by orthogonality relationship you can get it. Okay. So usually it's actually pretty straightforward because you only have 6 elements. Let's say you consider usually for one-dimensional representation, one is just for the number. The other is for something like a pseudo scalar. So usually you expect a negative value. And then this one is usually just for vector. You just consider vector. You just rotate the vector, then you'll be able to get it. Because this is a very simple example. A very simple example. You have a bigger group, then you'll be more complicated. So I think it's good that you do a few exercises to try to deduce the character table by yourself. But here I'm just want to show the property of the character table. Okay, so what if they are if they are the same? Okay, if they're the same. So let me just do one more example then. Okay, I mean this is a relatively simple, so probably I don't need to do it again and again. Okay, because you have 1, 1, 1, 1, then you have a -2 here. It's also orthogonal, so it's pretty straightforward. So how about we just use the same? the same column, just 1. Okay, so if you use 1, then what you will get is just the square of them. So just 1 square, 1 square, 2 square, you get 6. Okay, and the orthogonality relationship is h over ni. Ni is the number of elements. So this actually equal to 6 over 1 because there's only one element. Only one element. So what about the other one? What about this one? If you go to this one, then copy. I mean, the algebra are all very simple. It's just you need to kind of get familiar with it. Okay. So this one is 1 square, negative 1 square, and plus 0. And then what is that? That is 2. So 6. How many elements are there in the class? There are 3. So it's 6 over 3. Okay. I mean, you can do it one more time for this one. Then you just go and get it. Copy. Then you just use 3 here. Class 3. Then what's class 3? 1, 1, negative 1. So it's 1 square, 1 square, negative 1 square. So it will be 3. So how many elements are there in the class? There are 2. Okay. Then you get 2. Okay. So this shows the second orthogonality relationship. Is okay? I mean, the algebra is pretty straightforward. But when you look at the character table, you just know that those numbers follow some particular rules. Okay, some particular rules. Okay, so let's summarize. Let's summarize it. Okay, summary. Rule number 1. Okay. The number of irreducible represented IRs equal to the number of classes. Okay. So rule number 2. Okay, the dimensionality of all the irreducible representation square equal to the number of elements. Okay. And then rules number 3. Basically, this is sum of the square of nullity of all irreducible representations equals the number of group elements. Okay, rule number 3. Rule number 3 is the orthogonality relationship. Is K I K. And then here you have an NK here. So you have H delta IJ. So rule number 4 is something similar, but the second orthogonality relationship. This is sum over I, so sum over the representation, and then you have a K, you have a L here, then you have K and L. This one will be H over Ni. Okay, so these are the 4 rules. There's actually a 5th one in the textbook, but anyway, if you're interested, you can read it. But I think the most important one are these 4. Okay, 1, 2, 3, 4. You should. I mean, they're not that complicated. Basically, the first 2 are the most easy to remember. Particularly the rule number 1. Once you have a symmetry group, you just arrange them into classes. Then the number of classes is the number of irreducible representation. Okay, the most straightforward one. But it doesn't tell you the dimensionality. The second one is, if you have the dimensionality, you sum over them, then it will be the H. Then here you have the orthogonal two set of orthogonality relationship. So you can actually, by just using this 4, you can already deduce the characters of a lot of the groups. You don't even need to know the form of the matrix. I mean, one simple example is, I'm giving this example again and again. Okay. Oh yeah. Okay, let's go back to this example again. So this one, you have 6 elements. You arrange them into 3 classes. So you already know there are 3 representations. Then by using the second rule, this is the only configuration. You need to have, because all this must be integer, positive, non-zero integer. So the only way you can make this equal to 6 with 3 number is 2 squared plus 1 plus 1. That's the only possibility. Then you will know that in this group, you will have 2 1D representation and 1 2D representation. So you can already write. So once you know it, the first one will be identity representation. You can already write down all 1 here. The first column here, they correspond to the identity group elements. So you know this is the dimensionality. Okay. So you already write down these 5 numbers here. Okay. Then you only have 4 more. Then you think about it. You have a vector here. You need to find 2 more orthogonal vector. And for each vector, you already know 1 element. Then you look at here. Okay. Let's say you have 1, 1, 1 here. You have a 1 here. Then what number you put here to make it orthogonal? You have a 3 here. So basically, for example, you have okay, for the first relationship, you have for the first relationship, you need to have 1. Let me just make it x and y. Okay, let's solve this equation. You have 1 times 1, and then you have 3x. 1 times x times 3 plus 2y, you need to be 0. And usually those characters, they are integers. Then you look at what integer will be able to fulfill this relationship. Then you can easily tell this -1, this is 1. Okay, so once you get this one, then you just use this relationship. This is 1 times 1, this is -1, this must be 0. Okay, then you also get this 0. Then you will get this -1. So basically, you don't even need to know the exact form of this gamma. You can already write down the character table. You can do some exercises. Okay, I mean the algebra is pretty straightforward, but you just need to understand the concept. Okay. a lot of the time when we deal with group theory, we're just dealing with the integer numbers, but you can easily get lost in the analysis, because the concept is actually not as straightforward as you think. Okay, so why is the character table important? Why is the character table important? This is because they allow us to decompose the irreducible representation. Okay, suppose there is a reducible representation. Let's say gamma, okay? Let's say gamma, okay? So what do you mean reducible? Means gamma can be changed into a block form, of irreducible representation. Okay, let's say this is a gamma I or gamma J. Okay, gamma J. So we will write it like this. We will write this equal to AJ gamma J and sum over J. This is not the algebraic summation. This is a I mean this two matrices is a different dimension. Okay, so there's no way that they can equal. So this is not the algebraic summation. This is a way to show that this can get decomposed as the block form with this. For example, not algebraic summation. For example, okay, let's say gamma equal to gamma 1, and then you have another gamma 1 here, and then you have a gamma 2, then you have another gamma 2 then, okay? Let's say you have another gamma 2. I mean, gamma 1 and 2 are irreducible representation, okay? Gamma 1 and gamma 1 here doesn't mean they're exactly the same thing, but they are the same irreducible representation. Like this gamma 2 and gamma 2, when you write it down, the matrix element may not be exactly the same, but they belong to the same representation. Okay, let's say you have another bigger one. Let's say actually, I'm not very sure whether they will have exactly the same form on, but it doesn't matter. Maybe they have exactly the same form. Maybe they don't have exactly the same form. It doesn't matter. Okay, as long as they are the same representation. ... Okay, let's not ... Let's just make it finite. Let's say you have and all of these are 0. Okay, so here we will write it as gamma 1 plus gamma 1 plus gamma 2 plus gamma 2 plus gamma 3. Okay, so all you can write it as 2 times gamma 1, 2 gamma 2, and gamma 3. So when you read some paper, you see some equation like this. Okay, so what they mean is this. Okay, it's not an algebraic sum. This sum is basically means this is a reducible representation. By some similarity transformation, you can make this into a block form, and each block, and there are totally 5 blocks, and 2 blocks are gamma 1 representation, 2 blocks are gamma 2, and the other block is gamma 3. So what they mean is this, okay? And here I just write it in a simple way as this one. Okay, so when you read the paper, when you see an equation like this, then you need to understand is the meaning. The meaning is is that this is a reducible representation, can be decomposed into the block form, and each block corresponds to this gamma 1, gamma 2, gamma 3. That's the meaning of this equation, okay? Not the algebraic summation. Okay, so we want to know this coefficients, okay? Because these are just irreducible representation. We already know from the character table, just 1, 2, 3, okay? We all know. But this representation, if you have a representation, you want to decompose it into a block form. That is not an easy task. Because generally when you have a representation, you just have a big matrix with a lot of numbers. They're not in block form. So, but you know that it's too big. It is not irreducible representation. But you want to know what kind of block form can I make it into. If you just find a similarity transformation, that will take a long time. Okay, but you don't need to do so, because by using the character table, you can get this number quickly. You can get this number quickly. You don't need to do any similarity transformation. Okay, so first we start from here. If you get the character, so if you get the character, let's say the character, okay? Let's say the character for the R element, okay, will be equal to the character for the jth representation and R and sum over AJ. So why is this the case? So look at this one. Let me just copy this thing again, okay? Let me copy this thing again. So look at here. So let me see. Okay, let's put in some number. Let's say this is 1, 1. Let's say this is 0, 0, 1, negative 1, 0, 0, 1, negative 1. And this one maybe let me put it whatever number, okay? 1, 1, 1, 1, okay? Just identity matrix, right? It doesn't matter. Okay, these are the block form. So what is the total? The total character. What is the total character of this? The total character is 1 plus 1 plus 0, 0. Okay, plus 0, plus 0. And this is 3 plus 3. So basically, just the character for gamma 1 times 2, and the character for gamma 2 times 2, and then the character for this third one. Okay, you just sum over them. Okay, so you just get this equation. Okay, so we're going to get this A. We're going to get this A. So how do you get it? We are going to write this thing. Let me copy this again. And then we are going to write a I representation. Okay. This complex conjugate. And then we're going to sum over R. Okay, you do the same thing on both sides. You do the same thing on both sides. Okay, so let me see. You're going to have R, J, and then you have AJ. You just put the J here, and then the I is here. Then let me see. We're going to use the orthogonality relationship. Just put it here. Put it here. This one is the orthogonality relationship. You will get a delta ij. You get delta ij with the h. Okay, so you go back to check the orthogonality relationship. That is the relationship. Okay, so you have j, yeah, j, aj, h, ij. Then you just get h, a, I. So what is AI? So you just know that AI will equal to this thing over 1 over h. Of course, you can also change it into a sum over class. You can change it into the sum over a sum over class. Sum over class. And then x sum over class. But once you make it sum over class, then you need to multiply this number of class here. Okay, so basically, whenever you have a reducible representation, you take the character of the irreducible representation, then you multiply with one of the irreducible representation character. You sum over all the classes, and then take a 1 over h, then you get the representation. You get the representation. Is it okay? For example, let me just give you one example. So let's consider again this group. Okay, let's consider again this group. I think examples are more useful for you to get the idea. Where's that group? Where's the group? Okay, this is the group that we're going to use. Let me copy this. Okay. Okay, example. Okay, let's example. Okay, so let me remove all of this. Okay, in this example, you can actually write it out as matrices. You can actually write it out as matrices. So let me just write them out. E, you can write it as a. Let's consider one representation. Let's consider one representation. Consider a 2D representation. Representation. Let's say E equal to. I mean, these are group element. Okay. Let's say this would be the third one. Okay, the third representation. E equal to 1, 0, 0, 1. Okay. Then UA will be 1, 0, -1. Okay. So UB will be, it's just the matrix that you rotate a vector. Okay, it's just a matrix you rotate a vector. But let's say you have a matrix like this, then after UA, the vector become like this. So one of it flip. Let me see. Then it really depends on where is X and where is Y. Okay. Anyway, you just know it flip. Okay, one of it flip. Okay, that's why you have a -1. Okay, you can define that direction. Okay, so then this one will be more complicated because it is somewhat tilted. And then you see. Okay, I'm just copying the number from the textbook. Okay, so this are the matrix element of one representation. I mean, you can already tell that the character is 0, right? I mean, you sum over this is 0, right? Okay, I mean, here you have a 3, the third representation. So this character, the third representation. This is 2. Okay, this is 2. Okay, let's continue. Then another one is C3. C3 is this 1/2. 1/2. If you want to know why the matrix look like that, then you just draw a vector here, and then you just get the matrix, the rotational matrix for the vector. Okay, then you get something like that. Okay. 3. This is 2. Okay, so let's get the character. The character here will be you sum over will be -1, right? So this one is also -1. Okay, so you can already confirm what we did before. Let me go back and get the character table. Where? This one. Okay. Okay, this character table. So you can already see that we are getting this thing. Okay, because this class is this -1, is this 2. We get -1. The middle one here, this 3 rotation. This 3 rotation, we're getting 3, 0. And then here we're getting 2. I mean, they're all the trace. You can easily check they're all the trace. Okay, they're all the trace. They're all the trace. Okay, so now let's say we have another matrix that is bigger, another representation that is somewhat bigger. Let me see. It's not easy to write it. It's too big though. But probably you can treat it as an exercise, okay? Because we know that all of these are just 1. Okay, so all you need to do is this. Let me just copy all of them. You can treat this as an exercise that you do by yourself. You can see the 3D representation. Okay, if you can see the a 3D representation. All you need to do is just make it into a block form. You add a 1 here. Then all of them, you just, let me make it smaller. Just make it smaller. Then each of them, you just add one more block. Then you can test what I show you. Yeah. Okay, so you just make every one of them a block form. 1, 1, 1, 1. Eh, this is 1. I mean, it's kind of a naive example, but at least it's one example. Okay, so I hope that will. Okay, let's add a 1. Okay, so you have a reducible representation. You can easily make it complicated because once you do a similarity transformation on all of this matrix, the block form will be gone, and you won't know. Okay, so if you want to make it more realistic, you can do a similarity transformation to mess up the block form. Okay, so here we can remove this 3. It's no longer 3. Okay, it's just a reducible, a 3-dimensional reducible representation. Okay. Okay, so these are all the matrices of the representation. So you can easily tell that the characters already changes. What is the character? So the character here will be, this is 3. This will be 1, 1, 1. And this is 0. This is 0. Okay, so this is the character. So suppose now you do a similarity transformation. You use gamma and then add a u here, add a u here, change the coordinate to mess up everything. Then you won't be able to see the block form anymore. I mean, any similarity transformation can easily mess up this block form. Then you see just a 3x3 matrix that you don't know what the composition is. Okay, so suppose now you mess up the whole thing, but the trace won't be changed. So you will still get the same number. Okay, you still get the same number. So how do we know that it is gamma 1 plus gamma 3? We know that here this is gamma 1, this is gamma 3. Okay, how do we know it's gamma 1 and gamma 3? So let's go back to this character table. Okay, let's go back to this character table. So now we have a gamma here. What is the character? The character is 3, 1, 0. Okay, so just write it. You have a 3, 1, and 0. So how do you know the block form of this gamma? Then you just do it one by one. You just do it one by one. Okay, so we're going to use this relationship. Let me see. Okay, we're going to use this relationship. Copy. Okay, so okay, AI. So we're going to use this relationship. So let's do it one by one. Okay, so let's do it A1. Let's get the first one. Then this will be 1. Then let me see. So you're going to have this 1 times this 3. You're going to have 1 times 3 times this nk. Nk is also 1. This h will be 6. Will be 6, totally 6 elements. Then the second one, the second k is another class, is this class. So this one, I think I missed a complex conjugate here. But in this case, it doesn't matter. This one will be 1 times 1. 1 times 1. But you need to times this 3. You need to times 3. Then this will be 0. Okay, you get 0. So you times 2. Okay, so totally you get 3 plus 3. You get 6. So eventually you get 1. Okay. So let's do it. Do it for the second one. For number 2. Okay. For number 2. This will be 6. Okay. So for number 2, so you get 1 times 3, negative 1 times 1. Okay, just write it down. Let me just copy this then. I don't need to go back and forth. Okay. So basically here you have 1 times 3, this one and this one, plus negative 1 times 1, negative 1 times 1. And you need to times this 3 as well. And then here is 0. So 0, just 0. Okay. So eventually you get 3 minus 3. You get 0. So it does not include the second representation. Then we just do it one more time for the third one. I mean, the algebra is very simple, but I just want to demonstrate to you the procedure. Okay, so now let's go to 3. 3, and then okay, copy. So now we're gonna have this 2 times 3. 2 times 3, 0 times 1. And you need to times this 3. And negative 1 times 0 times 2. Okay, so eventually what you'll get is this 6. And this is 0, this is 0. So you get 1. Okay, so you combine together, you get gamma equal to gamma 1 plus gamma 3. Okay, is it okay? So you have a decomposition into the irreducible representation. Is it okay? This is important. This is important because later you're going to deal with one case that if gamma is an irreducible representation in group 1 in a group, then after symmetry breaking, G1 reduced to G2. Then gamma 1 becomes a reducible representation. In G2. So how will the degeneracy be lifted? Then you just get this. Then you know that this is a 3 by 3, so you have a 3 level. Then you will be lifted. You will be lifted into 1 is 2, the other is 1. This is gamma 3. This will be gamma 1. Okay, so in our previous case, for example, the d orbit, the d orbital is in a full rotational symmetry, it is a degenerate, because the d orbit has the irreducible representation in the full rotational group. So it has fivefold degeneracy. But after you put it into a MOS2, then the group is reduced. Is reduced into I think it's a D3H group. Then this one will become this summation of these three different representation. We will deal with more of this later. Okay, but basically, the physical meaning of this is when you break the symmetry, when this relationship is no longer irreducible, you need to decompose it into the new irreducible representation, and this represents how the degeneracy is broken. So the physical meaning is like that. Finally, I want to prove you one more thing, then we can end it. Okay, that is this relationship. This is a relationship that can be proved. Okay, but it will take some time. So, but I want to finish it so that we can make the lecture more complete. Okay, so just follow me. Just follow me, and the proof is not very complicated, but it take your attention. Okay, so let's consider. Okay, let's consider a so-called a regular representation. What is a regular representation? So for all the group, you can write something called a multiplication table. Multiplication table. What do you mean multiplication table? So basically it's like this. You have a lot of group elements. For example, here you have E, and you have UA, UB, UC, C3, C32. Okay, so this is the group. Okay, so you write the same thing here. UC, C3, C32. Okay, you write the same thing here. Then you're going to write down their product. You're going to write down their product. So what you will get is this will be E. E times E is E. This one, they're also E. So basically, you just get exactly the same thing because everything times E is the same as E. Okay, you just get exactly the same thing. Okay, so then UA times E, I mean UA times UA is also E, and then the this will be UA, and then let me see, what should I get? This will be C3. This will be C32. This will be UB, UC. Okay, so basically what you get is eventually you get all of this as E, E, E. They're not E. This will be, let me see, this will be C32, C3. Okay, so let me quickly write them down. Okay, UB, UC, and then C3, F, C, C3, UC, UB. Okay, I just copy. This is E. This is E. So this is UB. UA. And then what is this? C32. C3. UC. UA. UA. UB. Okay, so this is the multiplication table. Okay, so it's a bit tedious, but anyway, finish writing it up. So we're going to change this into another way. So because this one is the inverse, this one is also the inverse of itself. This one is also the inverse of itself. This one is UC the inverse. But this one is the this inverse. This one is the C3 inverse. Okay, what we're going to do is we want to write a character table. We want to write a character table that all the elements here are the inverse of the horizontal one. So we want to write something like this. So this is E. Okay, all of this we're going to write the inverse here. We're going to write the inverse here. UA inverse, UB inverse, UC, and then this is C3. We want to write the inverse here. Okay, so all of this doesn't need to change at all. The only change is that these two rows need to be exchanged. Okay, need to be exchanged. That's it. Okay, so what is the feature here is that whatever you have here, you have the inverse here. Okay, so you have all this E, A, B, C. So E, A, B, C, and then C3, C3, C32. But instead, you just make all of this inverse. Okay, so you have a character table. Okay, you have a character table. So now we're going to make a set of matrix that, let me say, it is called gamma, regular, E. So how do I make the E? So you just copy this whole thing. Copy this whole thing. And then whenever you see a E, you make it 1. Okay, whenever you see a E, make it 1, and all the other, you make them 0. You make them 0. You make them 0. And then eventually what you will get is let me write it here. What you will get is you just get all of this 1. And then all the other things are just 0. Okay. So you just get 0. Okay, so that is one matrix. Okay, let's get another matrix. We'll do a few examples. We'll just do a few examples. You immediately get it. So now let's get UA. If you're going to get UA, then all you need to do is make the UA 1. This UA is 1. 1, 1. And then all the other are 0. Where is it? Here. Okay. So you get a matrix like this. Okay, so remove this, remove all of them. Okay, so you get 0, 0, 0, 0, 0. All of them are 0. Okay, you get the idea. So you do the same thing for UB. Okay, you do the same thing for UB. Let me quickly get UB then. Okay, so you do the same thing for UB. Then you will where's UB? Okay, this UB is here. Okay, so you just make it 1, 1, 1, 1, 1, 1. All the other things are 0. Okay, you just follow similar strategy. You're going to get a set of matrices. Okay, so now we're going to prove that this set of matrices is a representation. Okay, is a representation. So let's prove. Basically, we need to know the relationship. You have a 2 element, let's say B and C, regular. We want to prove this. We want to prove if they follow this relationship for all the group elements, then they are a representation. Okay, so let's get it into a regular form. So how to represent this matrix element? This matrix element is denoted by a form like this. So basically, you can use the element to represent the indices. Okay, so you can write the element as AK, one of the element -1 times AI another. So these two are used as an index, as indices to denote the element in the matrix. Okay. So if you want to do it as a multiplication, then you need to sum over. You need to sum over AJ. This will be AK -1, and then AJ. And then this will be C. This will be AJ -1 and AI. Okay, so if we prove that this relationship holds, then it is a representation. Okay, so let's look at this element. What is this element? So according to our definition of the matrix, this element is 1 if this one equal to B. Because why? Because the way we set it is that if this thing equal to 1, we just set it to 1. That is our definition of the matrix. Okay, that's our definition of the matrix. If it is Z, then if it is they don't, if they are not M B, then it is sorry for my writing. If they are not B, then it's 0. Okay, so how can you make this finite? How can you make this finite? Okay, so this one is not 0 if and only if both of them are not 0. Like, let me see. If this is not 0, and these are not 0. because you're getting a product between them. So any one of them, if it is 0, then the product is 0. Okay. For some AJ, for some AJ. Just if, okay, just if, okay. Okay, so because this is the summation, if one of it is 0, then the whole product is 0. So if there exists a group element, so that both of them are simultaneously non-zero, then you get the finite one. You get a finite one. Okay. But how can this be non-zero? If this is non-zero, only if it's not 0 if BC equal to AK. So, but you look at here. But you look at here. For this condition to hold, so if this holds, that means this one B equal to AK J, this one C equal to, okay, then this one together, you can already get BC equal to AK. And this is just E. So you just get AK. Yeah. So that go back to here. Okay. So that means it is a representation. Okay. So basically, if the matrices are defined this way, fulfilling this condition, eventually when they make a product, you have this relationship, not 0. Okay. So it shows that it is a representation. Okay. So this shows that gamma regular is a representation. But of course, it is a reducible representation. The dimension is H, because it is defined by using all the matrix, all the group elements. So the dimension is H. Okay, next, there's a theorem. The name is very interesting. The name is called celebrated theorem. Okay, I mean, I don't know why they gave such a name, celebrated theorem. Okay, probably they're very happy that they proved something great, so they celebrate. Okay, it's called celebrated theorem. Okay, so let's decompose this irreducible representation. Okay, so let's say you have an AI. We have this formula, right? We just learned this formula. Okay. Then you have a character of this regular representation. Okay, so this AI will be the number of irreducible representation in that. So what is this? This one, if you take the E, you'll find that it will be H. I mean, you look at our definition, you immediately know. Okay, this is E. Okay, this is E. When it is E, what is the matrix look like? The matrix look like this. So the character is just H. The character just equal to H. But when it is the other elements, you can see all of this middle one are E. They will be 0. Okay? So from here, you can already see that the character for UA is 0. The same for all the other, because in the middle is Z, it will be 0. Okay? Similarly, all of them will be 0. So basically, this character will be H. R. If R equal to E. And for all the other elements, it will be 0. Okay? So that means AI will be equal to, because you sum over I, right? So you only need to sum over 1. So will be E. And X regular will be just E. And this is just H. So this will be E. So what is this? This is the trace of the identity elements in the ith representation. So it's just Li. It's just Li. Is that okay? So gamma regular equal to you sum over all the AI and then gamma I. Okay. So let me see. So this dimension is, so this one is this. So here, this one is just H dimension, H dimension, and this one will be like a block form. Like a block form. Let me see. It will be, I think a block form will be something like this. Oh no, it will be something like this. You will have what? You will have gamma 1. There's only 1. Gamma 2, there's only 1, because they are all one-dimensional representation. And the dimension is also the number of times that they will appear. Like this 1D irreducible representation appear only once. Okay? So this is gamma 3. I should use a different color. These are 2. Okay. So 2D irreducible representation appear twice, because AI equal to the dimension. Okay, equal to the dimension. So that means, what is the length of here? The length is Li squared. The length will be Li squared. You sum over I. You sum over all the I, and because each of this is Li, and you have Li of them, so the total length will be Li squared, and you need to sum over all the I. Is that okay? Like each of this has Li length, and you have Li of them, so it's Li squared. So like here, you have a dimension 1, and you appear once. You have a dimension 1, you appear once. You have dimension 2, then this 2-dimensional will appear twice. So the total length here will be Li squared. Okay, but these two are the same matrix. So these two must be equal. So eventually, you will get this relationship. So that finished the proof. Okay. Is it okay? Any questions? A lot of this numerical algebra, like with simple numbers. I mean, the algebra is not very complicated, but somehow the concept will kind of make you dizzy. I mean, when you go through the proof in group theory, is like that. A lot of indices here and there, and with just a very simple algebraic calculation, but somehow you just feel the whole thing is complicated, because the concept is not very easy to understand. Okay, so we finished this part. So as a summary, we still go back to these 4 rules. Let me go back to these 4 rules. Where are the rules? Okay, so this is the summary of our lecture today. So if you don't remember the proof on all those things, then you just remember this most important 4 rules. Okay. So let me go through it one more time. The number of irreducible representation is the same as the number of class, and then you have this relationship that I just proved. The square of the dimensionality of all the irreducible representations summed together equal to the number of group elements. And then we have 2 orthogonality relationship. This one is the primary one, and this one can be proved from this. So this one contains nothing new. It's just another way to express the orthogonality relationship. So I actually prove this by using this. Okay, but somehow as the rule, then we just leave them separately, list them separately. So there's only one orthogonality theorem. That is the great orthogonality theorem. All the other orthogonality relations are derived from there. Okay. So the fact that we use character, because the character remain the same after similarity transformation, and by using the character is already sufficient to decompose reducible representation into irreducible representation. Okay, so that decomposition relationship is important later when we deal with the degeneracy in a system with under symmetry breaking, how the degeneracy will change. And the fact that we only use the character, we can finish the decomposition. That make the character quite useful. Okay, any questions? Okay, if no question, then we'll end the lecture here. Thank you.